All right. Do we have any questions before we start today? Hopefully everyone has seen homework number 1 and started working on it. That is due Friday at noon before this class begins. Any questions on homework number 1?
That turned in person, or is that
Online. Homeworks are always turned in online on Blackboard. Any other questions? All right. So we're going to continue modeling, and today we're getting into mechanical systems. All right. So we've gone through different model types, specifically transfer functions is what we're going to be focusing on in this class. Now we're going to go over modeling a mechanical system and getting a transfer function for it, right? So for translational mechanical systems, in this course, we have a few assumptions that we're going to make. We're going to assume all masses can be represented by point masses, just to make it easier on us. Springs are ideal. And then for the most part, linear dynamics is what we're going to focus on. All right, so there are 3 important passive elements in mechanical, specifically translational mechanical systems. Who can name me one of them? Important elements of mechanical systems. Load.
Like a block, right?
A mass. How about just with a mass, right? A mass is going to be our first one, right? And so what we're going to go through is the diagram or figure for these, the parameter associated with the element, the dynamic state, the type of energy that element will store, and then relevant equations. All right, so for a mass, typically I'm going to represent it by some sort of square, rectangle, or just a point. All right, the parameter that is associated with a mass is literally the mass, units of kilograms typically. All right, now let's skip over dynamic state for a second because we haven't talked too much about that in this class, right? What kind of energy is stored in a mass? Not quite. Not potential. Maybe in some senses you could argue that mass has potential energy. Masses are associated with a different type of energy. Kinetic, right? Kinetic energy, right? What's the equation for kinetic energy for a mass? Mass times acceleration is not energy. 1/2 mv squared, right? I think I heard that different pieces in there throughout there, right? 1/2 the mass and then the velocity squared, right? That is the kinetic energy associated with any mass, right? Therefore, our dynamic state, the thing that's going to be associated with our dynamics, right? The thing that's going to have a derivative with respect to time in our equations for a mass is the thing that's associated with that energy, the velocity, the thing that's going to be changing over time, assuming our mass is a fixed parameter. Right? Velocity is our dynamic state, right? Because it relates to stored energy in our system. Okay, relevant equations. for a mass. There's one big one and we actually got it. Somebody answered it just for the wrong part here. Mass times acceleration, that's not a full equation, right? What does it equal? Equation means it equals something. Sum of the forces, right? What is that called? Newton's second law, right? Which is actually just a different form of the conservation of energy for a control volume. So mass times acceleration, instead I'm going to write the derivative of velocity, right? The rate of change of our velocity or state, because that's what we're interested in when mass is its velocity. That's equal to the sum of our forces. All right, that's our first element. What about another element for mechanical systems? Spring, right? I've given two of them to you guys up here. You know, that one moved for some reason. All right, spring is our second one. Usually represented by something like this, or sometimes I'll be lazy and draw it like a resistor. One of the two, right? What parameter? Well, actually, I'll leave this up to you guys, right? Any guesses for any of these boxes here for a spring? Right. Let's raise our hands for this one, just because I think it could get a little bit chaotic otherwise. For any of these boxes? K for stored energy. What is K? Spring constant? Does a spring constant sound like energy? No? Hands, please. Say. K times X. Okay, we're getting the right elements here. First, let's figure out where the K is going to go here. So K is not energy, right? It's a parameter for our system. It's kind of like our mass, right? What are the units of our spring constant K? Newtons over meter, right? We can see that is not quite the same as energy there, at least not in this context here. Okay. We have a few other things that people have shouted out here. Where do they fit?
Stored energy is 1/2 kx squared.
And what is that?
That's the energy stored in the spring at a certain compressed length.
Yeah, what type of energy? Potential energy. You guys really can't do the hand raising thing, can you? All right. Good. Potential energy is associated with our springs, right? You compress them, they have so much energy stored up. If you expand them, they also have so much energy stored up. All right. Other pieces.
Would the dynamics be displacement?
Right? So that X there, or I'm actually going to use D for the most part in this class, but X is going to work as well. Displacement in certain contexts, I think the proper way to describe it would be net deflection. D or X, right? In units of meters, right? The thing that's associated with our energy term. All right, the thing that's going to be changing our energy term here. Okay, last piece. Some relevant equations. Two, but I'm looking for mainly one from you guys. One that's been said already, again. F is equal to KX. What's that called? Hooke's law, right? The force of the spring is equal to that spring constant times X. It's really that net deflection. I'm going to use D here again. What about the rate of change of D, that net deflection here? That is the sum of our velocities, the two ends of the spring, right? Or sometimes we just call V net, right? Two relevant equations for our spring. All right, we got the two elements that are probably most common here. What's our third one? Third, damper. All right, damper usually represented by a dash pot. Looks like this, right? Okay, let's go back to the raising hands thing, just because again, we have 4 boxes to fill out here. Any ideas? Yeah.
And it was the
Divided by 2.
I have no idea where you're getting that from. It's interesting, but you chose probably the hardest box to start with here. So let's go with another one. Let's see, I want to get through. What, you want to try again?
Yeah, but a different box.
Okay, what we got?
B.
B?
For,
What is that? I'm going to use C instead of B. Well, what is that parameter? It's a damping coefficient, right? Units of damping coefficient, newtons times seconds over meters here. All right, that's our parameter, our damping coefficient. Now we get to the hard parts here. Any ideas for any of these last three boxes? One of them I think is easier than the rest.
Stored energy is equal to the damping coefficient times x, the derivative of x.
Saying something similar to what he just said. All right, that's an idea. So you're saying v squared, the derivative of x, right? Times c 1/2. Does that look right? Any other ideas? How about folks online? I know one or two of you were in my 3333 class. Maybe you guys can help them out. Nope, that's still not it. Folks online, any ideas? All right, folks in class.
I got an idea. Is it dV times displacement?
Nope. Nice try. The answer is a lot simpler than you guys think.
B times dx over
Nope.
dt.
All right, Rob. Thinking you say C. Nope. Simpler.
Nothing.
Dampers do not store energy, right? They dissipate energy. Dampers are like friction, right? Like drag. Dampers do not store energy, right? They are there to take mechanical energy and shift it into thermal energy, right? So therefore, if we don't have any stored energy, we don't have any state associated with it either, right? Simple, right? Dampers, just like resistors in the electrical world, do not store energy. They are there to turn it into thermal and throw it away, right? They are inefficiencies, right? Relevant equation, the force of a damper is going to be C times the net velocity, right? So we have three elements, two which store energy. That's where dynamics come from in these systems, right? If you have only a damper, based off of the simplified modeling process, we're going to go around here with ideal dampers, or I guess ideal damper, I'm not sure if that's the right terminology, but dampers are behaving in the way that we're going to assume where they're only dissipating energy. If there's only dampers, you're no dynamics to your system.
What is net velocity?
Net velocity is the two ends of the damper, right? This is going to create a force. This one's also going to create a force. So there's an effective force between the two of them, right? So you can move either end of a damper, right? You can think of it as like a cylinder and another cylinder with oil, right? There's a damping force if you pull it this way. There's a damping force if you pull it this way, right? The effective damping force would be the net between the two of those, right? So it'd be V2 minus V1 if you want to think of it like that, since there's only two ends. Okay, so dampers are like friction, right? So for our systems, right? It's a system as in it is being any mechanical system we're modeling, right? We'll have an input and an output, right? Our input often is the force F in units of newtons, right? It's an external force that's usually going to be acting on one of the masses. We can have different inputs for our mass spring damper systems, but I'm going to typically focus on that in this class, right? output can vary, right? Usually relates to velocity, displacement, position, or net forces even. All right. So our output's going to depend on our situation here. Often in this class, we're going to focus on force inputs, even though we could actually have displacement as inputs as well. Okay? Yeah.
This might be a dumb question, but I guess, it's been a while since I stored energy. I don't really mess with that. Can we just like, what is the application between stored energy versus just force power? You know what I'm saying?
So what are the units of force and what are the units of energy?
For
Right? A force balance is in units of newtons, right? Energy is in terms of joules. Joules are Newton meters, is that correct? Right? Two different units here. Actually, you are getting close to, if we were to take Newton's second law here and multiply both sides by velocities, we'd have the conservation of energy for a mass. The rate of change of, if we multiplied both of these times a velocity v here, force times velocity is energy, or it is power rather, right? And so we'd have power in minus power out is equal to rate of change of power, right? That's where Newton's second law comes from. It is conservation of energy. All right, so the recommended procedure that I have for you guys for getting a transfer function for mass spring damper systems and honestly, this is not the only procedure here. This is just what I recommend. So you make sure you check off all the major boxes here, that you don't make any dumb mistakes along the way. All right. The first thing that I would do is to identify what's going on here. Identify independent energy storage devices. And the states. All right. Our states, what does that mean? These are the dynamic elements that will have d over dt, right? The reason why deflection is a state is because it has a d dot there, right? The reason why velocity is a state has a v dot there in these equations, right? So if you have something with a derivative with respect to time, unless you're making a mistake, right? Though that will tell you what your states are for your system. Not super important, but for this class, but important enough. Energy storage devices. What are energy storage devices? Spring and mass, right? Masses and springs. What does independent mean? All right. How do you tell? If I draw this is a wall, this is a spring, this is a mass. Are these independent energy storage devices? Try again. Yes. This one has kinetic energy. This one has potential energy, right? They're two separate forms, right? However, if I draw another spring here, are those two springs independent? Right? Their deflections, their potential energy are directly correlated with each other algebraically, right? These two springs are not independent, right? So you can only have one state, or you only need one state to describe the energy in both of these, right? Same thing if there was a spring on the other side. Same thing if I had another mass and I bolted these two masses together, right? They have the same kinetic energy if they're locked together. Therefore, they would not be independent anymore. So you'd have one effective mass for the system. Okay? All right. 1B is to identify the inputs and outputs, right? Usually will be obvious or given to you, right? Step 2, use free body diagrams. To write out Newton's second law. Right, with all the spring and damping and all the external forces acting on the system. From there, write out the deflection dynamics if needed. And then from there, we're going to use the Laplace transform and get the transfer function. Okay, let's do a few examples, and that's what we're going to focus on for the most of the rest of today. All right, these are the general steps that I recommend. Are there other ways to get a transfer function? Absolutely. But this is the way that I would approach it. So let's start out, and we're going to do this through 2 ways. The way that I would prefer, and then the ways that most of you guys have probably learned at this point here. All right, so for this example, we have 2 outputs for the following system. And 1 input, which is going to be our external force F. Find the 2 transfer functions. All right, so there are multiple ways to go about doing this, but we have a spring attached to a mass here. That mass has a force acting on it, F. This is K. And let's add in our damper for good measure here, C. All right, I'm also going to say that output number 1 for our first transfer function is going to be the deflection of the spring. And output number 2 is the velocity of the mass. Okay? All right, so let's start out with step number 1 here. Step number 1 usually just involves taking this figure, redrawing it if you need to, though that's not always necessary, especially depending on how much time you have. Right? And then we're going to just start labeling things for it. So what variable have we typically used for our input? I should more correctly say our control input. What symbol do we use for that? U, right? And then we have 2 outputs, right? Which we're going to need to take a second to actually define here, right? So how do we recommend we approach this figure here? What do we need to label? Based off of identifying our independent energy storage devices, our states, inputs, and outputs. Just our input. How many independent energy storage devices do we have? Heard 2, I heard 3. 1, all right, now we've got 1, 2, and 3.
No,
Okay.
it's 2 because they have a mass.
Okay, so I agree with that logic here. It is 2. We have a mass that stores kinetic energy. We have a spring that stores potential energy, right? Automatically, springs and masses, unless there's something weird nonlinearity thing going on, those are independent right off the bat, right? So we have at least 2. Does the damper store energy? No, right? So that doesn't have any energy associated with it. So we have two independent energy storage devices. Let's identify what our states are for this and label them in this figure. So what are our states? How would you guys draw them out?
That where you define variable with like the lines and arrows.
Yeah.
So like the function.
Yeah, so velocity, I'm gonna draw out like this. Sometimes I'll put two arrows, right? Velocity is associated with our mass, right? Now, for our spring, there's two ways to go about it, right? I bet a lot of you guys do, this is X and this is X dot, right? That's perfectly legitimate, except you would actually end up with more states in your system than you should, at least in terms of like state space modeling here. For the most part, that won't be too much of a concern for you guys. But I'd like to go through an example to show you how I do it. I define the actual deflection of the spring, right? So the spring is at its nominal length, right? And if the spring edge over here were to move because of the mass, that would increase its deflection, right? And if for some reason, whatever we have, right, the spring edge over here were to move because the wall moved, right, that would also change its deflection, right? So I typically like to do things in terms of its deflection, but you also could do it in terms of X and X dot here, right? So maybe we'll try and do both simultaneously. All right, what else do we need to do for step number one here? We got our input, we got our independent energy storage devices, and thus our states. What are we missing? Say again? Did somebody whisper it? I still hear him hearing whispering. Which is? And we did the input, so what we need to do? All right, so we have two outputs, right? Y1 and Y2, right? Should these be? You gotta speak louder, man. You have no idea. Right? It's said right there, though. S? I don't think we have an S yet. K times X? This is the basic problem, guys. It's simpler. Read it. Output number one says deflection of the spring. D or X, right? They are the same thing in this case. Output number two. X dot or V, right? Same thing in this case. Okay, that's step number one. Step number two, free body diagram, right? We draw out our free body diagram here, right? We already have that force U acting on this system, right? Probably not a bad idea to define your velocity, positive direction here, right? Or X dot if you want to. Right. And the way I like to do free body diagrams, I pretend I'm holding every single mass in place except for one, the one that I'm doing the free body diagram for. I move that one in its positive velocity direction, and I think about how are the forces going to react, right? So if I move our mass in the positive velocity direction here, what kind of forces are going to occur on our system? K and C are not forces, but you're on the right track here. So we have KD, right? The spring is going to extend, right? The spring extends, what happens? I'm looking for the simplest answer, right? It pulls it in what direction?
The opposite direction.
Right? So we have K times D, which is again, K times X in this case, it happens to work out the same thing, right? Okay. That's the first force that's acting on our system. We move that mass to the right. The spring says, no, come back, right? What's our second force? CV or CV dot? Which one? C times V, right? And again, a damper is going to resist motion. It's going to fight against it. So if I move this mass to the right, just like friction, it's going to try and slow it down and stop it, right? Okay. So we write out Newton's second law here. What does Newton's second law state? You guys are all whispering, let's, now you guys are all whispering together, that's all helping. All right, you're at least vocal, but I missed the first part, so say it again. So let's start out with mass times acceleration, right? Is equal to the sum of the forces. So let's start out with mass times acceleration. How could we write that out? mv dot, right? Or mx dot dot or x double dot, right? Sum of our forces, right? You said two of them, right? So KD and CV, right? What sign should those all three? Well, we have also the external force here too, right? So which ones are positive and which ones are negative, right? Why is U positive and why is KD and CV? But yeah, why not having U negative and then the other two positive? We picked it that way. What does that mean? Same direction. Not as you got to be careful here. What if I said there was a second force F2 here that's going in the opposite direction? It's the velocity, right? I think that's what you were getting at, right? We happen to choose velocity and U going in the same direction as each other, right? But it's the direction of our velocity. So anything that's going with our velocity is positive. Anything that's fighting against positive velocity becomes negative, right? We can also write this out as U minus KX minus CX dot. Right. Step number 3, which is to write out the deflection equation. That is only relevant for this one right here, since we're not dealing with deflection in the second one. But if we needed to, D dot, the rate of change of that spring's displacement, right? One side is a wall, so that's not going to change at all. The other side is our mass's velocity, right? So one side of it's going to move with our mass, the other side isn't going to move at all here. Okay? And then our last step, most important one, let's get our transfer functions. Right? Actually, we need to get 2 here because we have 2 outputs and 1 input, right? So we're going to get one transfer function from the input to U1 or Y1, and we're going to get another transfer function from U to Y2. So let's start out with focusing on Y1 here. That's the easier one. Okay. So what do? Laplace transform. So I'll do it for the one that you guys probably prefer for now. Mx double dot is equal to U minus KX minus CX dot. Right? Do the Laplace transform of that guy. What do we end up with here? MS squared, big X of S, right? Okay, let's stick with what we have here, but you're getting ahead, right? Which is good, right? Assuming 0 initial conditions, right? Typically, we're going to ignore them unless I say specifically not to, right? In the real world, you should always be paying attention to your initial conditions, though. All right, so what do we have on the right side here? You want to just continue? U of S.
Yes.
Mm-hmm.
Minus KX.
Right, Laplace transform of these, assuming IC's equal to 0, which I'll usually say at the beginning of the problem, at least for the first few lectures in this class, right? Okay, we have this. We can solve for X by moving everything over. MS squared X of S plus CS X of S plus KX of S is equal to U. All right, let's just group all those X of S's together. All right, what do we do from here, though? X of S over U of S, okay. So X of S over U of S is going to be 1 over ms squared plus cs plus k, right? Okay, what else? Are we done? We could say potentially we're done here, right? If we recognize one thing, what was the transfer function we were looking for? Y1, right, which happens to be x in this case, right? But what if the transfer function we were looking for was an x? Like with y2? What would you do in that case? How do you get y2 of s over u of s?
Y1 was referring to the function.
Mm-hmm.
Y2 the derivative of Y1.
Mm-hmm. So what is y2 equal to? X dot. So maybe let's do a Laplace transform of this guy, right? Y2 of s is equal to s x of s, right? So y2 over u is the same thing as s x of s over u. So in this case, right, because they're derivatives, one versus the other, right? Same thing as the other one, but with an s on top. All right, we already had x over u, that was this guy. All right? That one makes it pretty easy. But this isn't the easiest case, right? Not always. And there could be a lot more complicated expressions and requiring you to go back and figuring out now that you have x of s solving for something else entirely. This is a basic example. Any questions?
So when you ask us, say for instance, I was in the notion of this solving for y1s. So do we need to solve for both in that instance?
Well, if I say there's two outputs, give me two transfer functions, you need to give me two transfer functions. Otherwise, the problem's only half done. Or maybe 2/3 done, depending on where you sit. Typically, we're going to deal with one input, one output for the most part, but there are some cases where we won't. Other questions? All right, let's do another example. All right, and so another way, by the way, what we could have done here is I could have done a Laplace transform of d of s is equal to v of s. And then the Laplace transform of this guy would have been, or rather, this guy would have been m s v of s is equal to u of s minus k d of s minus c v of s, right? And I could have solved those simultaneously for d or v in that case, right? That would have been another way to go about doing it. Solve simultaneously. All right, another example. We'll see how far we get with this one. We'll at least start it. So now let's say we're going to have two masses and two springs at least. And typically, I just ignore gravity in a lot of these cases. I'll say ignore gravity, ignore friction. Those will have some effects, especially if we have like a inclined or a vertical system. But for now, I'm trying to keep it simple. This is K1, this is K2. We have a damper C1, another damper C2 here, right, and a force F acting on our system. All right. And so for this problem, F is the input. Output is deflection of the first spring. But we will adjust this problem later on and say second output is deflection of the second spring. ICs are 0, no friction. Don't worry about gravity or any horizontal motion or any vertical motion. Rather, we're only going horizontally here. All right. So we want to take this system and we want to get a transfer function for it. Let's go through the same procedure again. So I'm not going to help you guys out. I'm just going to say no when I think it's wrong. But you guys get to lead the way with this one. So how do you want to do it? We don't even necessarily need to go the step-by-step process that I did before. You want to start with the free body diagram? All right. Well, for which one? I'm going to put both here. Okay. All right. Somebody else. Parameters. Okay. What are our parameters? So I'm going to stop you here just for a second. You're not looking at parameters. You're talking about states, right? Parameters are K1, K2, C1, C2, M1, M2, right? Those are typically constant, right? You're talking about the things that are going to dynamically evolve over time. What do you want to go with for these? Now, when I say D, I usually mean a deflection. I write it like this. And that represents that the spring moves either way, right? That deflection is going to change, right? Is that what you're intending for here? So you can do it. You absolutely can do it this way, right? I'm going to bet that half the class in here isn't going to do it that way, but you think like me. So that's good, right? So I'm going to, well, I don't know if it's good, but good or bad. The two deflections, right? What else? Velocities, right? Where do you guys want the velocities to point? So I want you to be careful about your language there. They both will go right. No, you get to choose, right? You could choose one going left, one going right here. It doesn't matter. That force, and this is something I notice a lot of people do, right? They always try and define things in terms of the one force that's acting on the system, right? But that's not true. The equations will work out if you have the velocities going any direction you want, as long as you are consistent throughout everything that you're going to do here, right? The same thing with currents and voltages. You just need to choose a sign convention and stick with it, right? Because if I add in another force into this system and it's pointing left, a lot of students used to get confused by saying, well, do I choose a velocity going left or right here, right? It doesn't matter. You just need to be consistent. Okay. So we've defined our states now. Now what? Somebody else. Okay. All right. So tell me what forces to add.
M2, we have force.
That's F.
Then we have force,
There's two springs.
K2.
K2.
Is D2 relative from that one mass, or is it relative to?
D2 is the deflection of the spring. So the spring has a normal length, right? And when it's at that length L, it doesn't have any potential energy. But then if I were to take that spring and pull it one way, its deflection would increase. If I were to take it this way, its deflection would also increase, right?
Is that like absolute to position in like space?
It's in a sense, but it has to be both endpoints are absolute, right? So it's really the net change between the endpoints, right? And so a positive deflection means that this endpoint and this endpoint spread out further, right? But that could have meant this one went over here, but this one went way over here, right? That would still be an extension to the spring.
Okay.
All right.
Then K2 times 2 pointing in the opposite direction.
Wouldn't it be D2 minus D1? Because they're both dynamic bodies.
If I drew this as in x1 and x2, the x's would have it. But what is D2 defined here? D2 is x2 minus x1. That's what I was just discussing here. That's what you guys are thinking. You guys are thinking in terms of absolute positions of the masses, and I think in terms of deflections of the springs themselves, right? So it would be KD2, but D2 is x2 minus x1. That is the net deflection on the spring, right? Right? That, well, I'm trying to clarify it for you guys here, right? That's the difference, because I heard a lot of like groans of like, oh, that should be it, right? It all depends on your coordinate system. I like to work in terms of deflection, but maybe you guys are more comfortable in terms of these x1s and x2s and positions of the masses. That's okay, but there are some certain situations where you'll end up with a higher order transfer function than you actually should. I think it should simplify down, but sometimes it ends up being a little bit more complicated than you need it to be. All right, somebody else help me out with mass number 1.
I have a question.
Yeah.
The damper, would that be V2 or is it like a net velocity?
What do you think?
I'm inclined to say net velocity because we talked about like you have two endpoints and it's their net.
I would agree, right? So if that mass moves to the right, the damper is going to try and fight it with C2, V2, right? But what happens when the first mass moves to the right? That damper is going to try and push the second mass out, right? It wants to get back to its position where it's not moving at all, right? Right, that's our net difference here, V2 minus V1, right? They're fighting each other, right? It's just like a spring, except it deals with velocity instead of position, right? If you have two masses, right? And this one, and there's a damper in between them, this guy moves over here, the damper is going to try and force this one out this way. All right, so we do need that piece. So K1 is connected to a wall here, right? So we got to factor that in, but let's start. Let's work on this first mass here, our free body diagram. What forces? Give me one.
A1. Or A1.
And what direction is this pointing? K1 times D1 or K1 times X1, because that other wall is never going to move, right? So X1 and D1 are the same in this case. What else? C1 times V1 to the left, right? The net velocity, the wall doesn't matter, right? So it's just going to be V1. Any other forces that act on the system? On, say it. K2, D2, right? Equal and opposite forces. What else? I'm going to assume that you guys said it right. I heard whispers. All right? Equal and opposite forces acting on this system. Okay? We're running out of time here. I will post the full solutions online, but what will we do next from this step? Break it down for me.
Right on.
Sum of the forces, Newton's second law, right? And then Laplace transform. If you're working in terms of the D1s and D2s, you need to have D1 dot is equal to something and D2 dot is equal to something. Full solution will be posted online, as well as another example I won't go over, but you guys can at least try and work on it on your own.
I know this is crazy.